Okay, sorry. Can you see the slide? Hello?
Yes, ma'am.
Yes.
Okay.
Yes, ma'am.
Fine. So today, so far we have discussed about modeling, different strategies of how to model different embedded scenarios. So from today onwards, we will be focusing on the design part. For design, we know when we are trying to map our model to some processor, we have to know that what types of processors are available and what is our requirement. So how can we map our requirement to existing processors? So for that, we understand that for embedded scenario, we do not typically use general purpose processing, right? Okay, before that, I just wanted to ask, so some of you all are having, you all are coming from different, either some of you are from EC, some of you are from electrical. So have you done any course in computer architecture?
Not yet, ma'am.
No, nothing. Okay. Okay, fine. So for general purpose processing or general purpose computing, this, wait. So Intel x86 architecture, that was name, that is very known. Okay. But we will see later on. Someone asked, I remember maybe in the first class, why why this x86 is leading in some scenario and why ARM is leading in some scenario. We will see in some cases x86 is also important in case of embedded design. But that is, we will come to that part. But what is the general idea is we require two types of processing, or we have two types of processors. Like one experiment is general purpose processor. For general purpose computing, what does it mean? It supports variety of instruction sets. Okay. And for embedded applications, we have huge variety of processors, but they are typically made for some specific task or specific applications. So we will see one by one what are the advantages or disadvantages of each of them, or limitations, we should say. What are the advantages, and in some cases what are the limitations in each of the cases. Otherwise, see, variety of processors can be daunting to a system designer, because when you have some specification and you have done your modeling, now you have to map to come to the design part. You should have the idea, should have the knowledge about different types of variety of processors. Otherwise, you will never know properly, or what to say. Definitely to which processor you will map your specification. Now, this is quite known, I think, quite understandable, that general purpose computing is most of the cases we do not use this general purpose processes in embedded scenario. Or if I reframe the question in other way, main idea can be that can I use this general purpose processing in embedded scenario? Because when we are coming to the embedded application part, our main objective is that a dedicated function implementation, dedicated scenario, specification implementation. So for that implementation, it may happen that we do not need variety of instructions. Maybe if we focus on a targeted domain, if we focus on a targeted set of instructions, and if we add some features that may improve the performance, that may improve maybe storage or some other features related to that domain, that will be more advantages in case of embedded domain. Okay. So maybe we can think of performance, we can think of power scenario, we can think of storage. Anything is possible, because when we are talking about embedded system, embedded domain, everything is constrained. We have some real-time requirement. We have the requirement that I have to come up with a design with some particular power limitation, power restrictions. I have the limitation of storage. I cannot use huge hardware, I cannot give huge hardware supports to design my embedded application, because that will again incur huge size. So in most of the cases, I have to come up with a space constraint scenario. So considering all this, it is not always that we go for we choose general purpose processing in embedded scenario. But that is not true that we can never choose general purpose processing for embedded domain. So for that, we have to evaluate different types of processes in terms of their ISA. ISA means instruction set architecture, and how we are realizing that processor in the final platform. So initially in this class, we will mostly concentrate on this ISA part. Okay. What we mean by ISA? Instruction set architecture. It is a set of basic instructions that a processor understands. Okay. Boundary between, we are telling that software and hardware. What does it mean? Take a simple example. Maybe you have your anything, maybe in a GCC platform or embedded C platform, whatever platform maybe you are choosing, whatever editor, whatever platform you are choosing, you have written one C code. Okay, that is your software instructions step by step. Or choosing any microprocessor, microcontroller, you have written your embedded, you have developed your embedded software. Development software means what? We know software means nothing but few set of instructions I have written that I expect that if they execute, they will give something as per my requirement. Now what will happen? My computer is having, we know that having some components like CPU, some processing unit. I have some memory. I have some input outputs. So how this instructions, software instructions are getting mapped to this back-end hardware? How it is getting mapped to this central processing unit? And from the central processing unit, how it is actually fetching values from memory, and then it is doing some operation, maybe whatever trivial operation it may be, maybe some simple addition, simple multiplication, whatever it may be. How my system, my embedded, not embedded, sorry, my processor is understanding what I have written in my software instruction. So basically this instruction set architecture is bridging the gap between this software code set of instruction, whatever you name it, whatever I have written, to the back-end hardware. It is the boundary, it is the bridge. Okay. So when we say this types of instruction set, okay, what is this types of, what are the different types of instructions or instruction sets? We will see that first we can name it RISC. Maybe you all heard about RISC and CISC. These two names are very common. So in RISC there are different properties. Maybe most of you know all this. But what is the main difference between RISC and CISC? That in RISC we need fewer cycles per instructions, and in CISC what we need? Fewer instructions per program. That is the main difference. What does it mean? We are trying to write same specification to this one to RISC processor, one to a CISC processor. So the number of instructions, whatever I need in case of CISC, for the same specification of the same program. That is sys. In case of sys, that is lesser, fewer compared to RISC. Why? Because see, RISC, you can think that instructions are comparatively simpler. That's why it requires fewer cycles. Per instruction, the number of machine cycles, I think you all know about the machine cycles. So the fewer cycles required per instructions. So this is the main idea between RISC and sys. There are many, we will come up later. Just from the name, we can understand that. Next, minimal instruction set computers. What does it mean? When for this type of computers, or processor, you can think, whenever we are choosing number of instructions, the very small number of basic instructions we are choosing. Okay. Very small number of instructions means we will see whenever we are storing these instructions and we are trying to map them with the backend, that is done by these opcodes. So less number of instructions means less number of opcodes. I'm not talking about opcodes now. We will talk in detail in the later slides. Okay. So of course, what you can understand, what is the typical advantage? Smaller instruction means we will see when we will opcode, you are searching for typical instructions or you are selecting typical instructions. Those are faster, and again those are basic instructions. That's why that will lead to some faster operation for specific case. But disadvantage is that you have to restrict your specification or your implementation in those specific basic set of instructions. So when you will go for this instruction level parallelism, okay, forget about it now. You will understand by your own. We will explain this in detail. What we mean by instruction level parallelism. As of now, you understand, for RISC, we require fewer cycles per instruction. For sys, we need fewer instructions per program. And in minimal instruction, we have chosen few basic instruction operations. Next, this is very long instruction word. This one also, we will take one example of this, then we will discuss this, because at this point, I think you will not understand much about this instruction level parallelism. We will discuss this instruction level parallelism, and then we will come back with an example of this VLIW. So just know that this type of processor or this type of instruction set, they support good amount of parallelism. You understand, parallelism means good amount of parallelism means good amount of, improvement in terms of performance. Okay. Then explicitly parallel instruction computing. That means you have some compiler that is explicitly supporting some amount of parallelism, and that is not directly, you are not thinking when you are actually implementing this type of parallelism, you are not thinking about the backend hardware. You are doing this based on some software instructions supported by some special compilers. Okay. So when we will discuss this instruction level parallelism, we will again come back to these two, we will again come back to these two, and we will take one example and we will discuss. Now to very interesting type of processors or computers. I don't know whether you have heard of it or not. One is zero instruction set computer. So what does it mean? See, when we are designing any computer, any processor, my main purpose is it will process something. How will it process? I will give some instruction, and based on that, it will process. So if I have zero instruction, then how the processing will take place? Then why to be specific, why we are calling it at all a computer? Because maybe in classical sense, we are not storing any instructions. storing any instruction, or we are not considering any particular instruction, but we are doing some pattern matching, and that way we are performing some processing. So these type of computers or processors, we term it as zero instruction set computer. Is that zero instruction reduced? Okay, another slide maybe. Okay, this slide will come later. Sorry, this is another type of instruction set. This is called the one instruction set computer. That means you have developed one processor or you have developed one computer that is only having one single instruction. What does it mean? Does it mean that you are capable of just doing one single instruction only? No, that is not the case. In case of one instruction set computer, what we do, we just allow one single instruction like move, like subtract and branch if less than or equal to 0. So this is one typical instruction that this one OIC supports. So what does it do? This subtract and branch means, let's say you have A, B, C, okay, 3 operands, and you are checking B minus C, that is, maybe you are considering this B and A, those are some specific memory locations, okay. So you are considering whatever data you have stored in that specific memory locations in mem A, mem B and mem A. So you are computing mem B minus mem A and you are storing them in mem B. Okay. Now in the next part, you are checking if this mem B, I mean, now this is the content of this mem B is less than 0, then you will perform one jump operation. That will, you will go to some another location, that is go to C. Okay. So this is the basic idea of subtract and branch if less than or equal to 0. Okay. So this is not typically there are different types of YSCs. I've just taken these example. Now if we consider this single instruction, you can see here using this single instructions and manipulating just this single instruction in different steps, you can actually implement add, not, and all possible instructions. Okay, so this is the concept of one instruction set computer. It is not that one instruction set computer means I can execute one single instruction. Yes, I can execute all type of instructions, but realizing them or mapping them to a particular single instruction. Okay, so this is the basic idea of one instruction set computing. So now I think we have some idea that when we are talking about instruction set or instruction set architecture, it is not that we are just having one type or two types with CAD6. We have many typical architectures, we have many typical processes. So we must have the basic knowledge that what this instruction set architecture means and how we can map them to our CPU, to our memory, how I can store the operand, and how from whatever I have written in form of my instruction, how I can map them to my backend hardware. Architecture, backend hardware. Okay. So for that, let's revisit this MIPS ISA concept once again. Okay. Let's see. Okay. Now this is about, we will be talking about this. Wait 1 second. Yes. Instruction set architecture. You can see here what is it is written. It is written that how to talk to computers if you are not in Star Trek. That means you are writing some instructions and how through those instructions you are talking to your computers. So where I have to put this instruction set architecture, as I have already told in the previous slides, that instruction set architecture is basically a boundary between my hardware and my software. So exactly this is the this diagram tells the same thing, that you have developed for your application. You have written some soft code to your operating system. You have done the compilation. You have in your you have done the compilation, and up to this part, your operating system is taken care of. Now, from your compiler, whatever values you have got, you have to send them to your hardware part. Okay, there you have your actual design, backend design. Now, you all have written any C or any Java code. Can you tell me when the compiler outputs you have done, and you have the your compiler outputs, what is the form of that output?
Binary files. Ma'am, is it binary files?
Yeah, binary files. Though we generally term it as machine code, right? Okay. So we have some binary files. They are nothing but 1 or zeros. Now, after doing this, you can check with these vocabularies. Maybe I'm just skipping this part. I'm coming here. Okay. So I have written some set of instructions. That is my program. I have compiled it, executed it. Now some of my binary file, compiled it, and that binary file I have stored in some memory. Of course, I'm storing somewhere means I will store in the memory. After that, when I'm trying to execute that, what will be the cycle step by step? So I have to fetch the instruction. Okay. When I'm fetching that, I'm in this state. I'm in this state. Yes. In this stage, I'm fetching some instruction from my memory. Okay. And then, of course, they are 1 and 0, nothing but some strings of 1 and 0. I have to understand how I will decode that. How will understand if the same instruction, whether it is telling the hardware to do some addition, or it is telling to do some multiplication, or whatever possible operators you have added or you know. So maybe from this decoding part, we will come step by step that how I will know, how I will decode. But once I have decoded that, I know that, okay, this instruction signifies that I have to do some addition or multiplication. Now I have to know that on what operands. Like I know I will do addition, but on which values I will do that addition operation. For that, what I have to do? Operand fetch. Again, I know that is stored in the memory. So for that, for these step instruction fetch and operand fetch, I have to know what is the address of that operand that I'm interested. What is the address of my next instruction that I'm going to fetch? And secondly, how they are stored in the memory and how I can access some specific part of that instruction or those operands. Okay. Then I got everything. Maybe after this stage, I got everything. I know I have to add. Maybe I got my two values, 3 and 5, and I know from this decode stage that I am going to do some addition, and then I will do this execute. Okay, I will do this execute. Execute means I will do the computation. For this computation, whatever I want to execute, directly I should have the support from the hardware, right? Because if I want to do some addition, of course, some adder will be present in my arithmetic logic unit part or ALU part. If not, let's say I'm trying to do some complex operations. Let's say I'm going to do some typical multiplication or exponent computation, and I do not have that support, that direct module in my hardware. So what I have to do, I have to break my instruction, my operation in such a way, maybe exponent computation I can break into typical few multiplications, such a way that that multiplications can be supported by whatever module I have. Because in spite of the fact I'm writing software, I'm executing in form of a software instructions, simply writing few instructions. In the back end, whatever I have, there should be a mapping between with my hardware and my software. Then I have to store whatever I have found, that is my result. I have to store it back to the memory. That means to do that, I have to know about the memory organization where I will store. Then I have to again, I should know in my memory where I have my next instructions, or how from this instruction I can access my next instruction. So this is called a typical instruction execution cycle. These are the few steps I have to follow always whenever I have stored my compiler output in my memory. Memory means where I will store it. Remember when we have talked about our basic components of our system or computer, we have talked about something like instruction memory and data memory. So in that way, we can assume if my memory is separated, from the instruction memory I have to fetch this instruction part, and from my data memory I will fetch this operand part, and I will pass them in form of control, in form of data. I will pass them to my execution part, that is my ALU, and then I will store the result back to the memory, or maybe in some cases register, based on our requirement. Based on, again, where I will store back the results, that will be defined by this instruction decode part, because that instruction decoding will tell me what to do, on what to do, and where to store the result back. So these few steps I will see, when we are talking about this instruction set architecture, after ending this discussion, we should have the clear idea that whatever instructions I have written, whatever my compiler output was there in form of 1 or 0, what they are actually doing in my backend hardware. Okay, so these are the few answers we will try to give. So this is what they have jotted down. These are the few questions, that what operations and how many operations we are doing, on which operands we are doing, and finally, for the other results, I have to understand how I will store this instruction and what may be the formats of storing those instructions. So let's start with this first. Now this instruction length, when you are storing, your compiler actually maybe they created some 10 output. Maybe if you have 4 instructions, 1, 2, 3, 4. For each instruction, it has created some 10 sequence, right? Now, first question will be, will that instruction length be variable or maybe fixed? So, of course, we understand if it is fixed, it gives us, some amount of restrictions, but there are, in case of designing perspective, it is comparatively easy. In case of, there are different examples of variable length instructions also, due to some added requirement of flexibility. Okay, I'm not coming to, this point, just you should have the idea that we can have instructions of maybe fixed length, maybe variable length. And we are starting our discussion with this mixed instruction or mixed processor, where we have this 32-bit instruction. We are considering 32-bit instruction format. Okay. So when we are talking about this instruction format, what we can expect, what do we have? We will have some opcode. Okay. Opcode means what? Opcode means it is directly your mapping of your instructions to your binary. Like if you are instructing to your hardware to do some addition, you are writing the opcode map to that addition. For subtraction, opcode map to the subtraction, and so on. So these are, what to say? Opcodes are actually specifying what operations you have to do. Okay. Next, these different fields, like you have, this is, let's say it has shown about VAX level, but maybe you are considering if MIPS, you have 1011, these are 32 bits. So how many, these first few bits will give you the idea of opcode. We will see what does it mean by the rest of the bits. In some bits, it will give the address of your operands from where you will fetch. In some cases, it will give index. But everything is dependent on these type of MIPS instruction formats. Okay. So see, we have considered 3 types of instructions. Actually, typically we tell this. What happened? So we consider this R type of instruction. This is I type of instruction. This is J type of instruction. Okay. What does it mean? This is register type of instruction, where here opcode is giving you the idea of what operation you have to do. In general, this RT and RD is giving you the address, register address of your input operands. This RS is giving you the output, address of output register. Okay. This is shift amount. Okay. And this is some associated functions. Functions, right? Like maybe this opcode is telling you that, okay, do this shift left, or do this some subtraction. And if this function may be associated with this opcode to typically specify what type of subtraction you want to do. Okay, so this is maybe extension of this opcode when you cannot specify your full opcode specification in this 6 bits. Okay. Next, this is immediate type. In immediate means, here see, you have, this is your destination register address. This is one source register address from where you are fetching the operand, and this is immediate. Immediate means whatever there the value, maybe you can write this way. If it is #40, that means you are just taking this immediate value, you are computing that value with the whatever value you have stored in this register RT, and if your opcode, let's say it is multiplication, you are multiplying these 2 values and you are storing this answer to this RS, register RS. This type of J instruction format we typically use in case of jump instructions, where your opcode suggests that you have to jump and this is your target maybe location address, so where you can make a jump. So this way, here one example is given, opcode 0. See this, if you are actually dealing with this type of addition instruction, okay, their opcode is already given 0. The function, some extension is given 32, some which type of addition you are going to do. Values, this is the register for destination address and there is no concept of shift about, so that is 0. So when you are actually reading this, I mean not you are reading, your hardware is actually reading that these 32 bit, it is immediately getting the idea, okay, first 6 bit, this means this is my opcode. Opcode is 0, so that opcode maybe corresponds to your addition operation. Then next 5 bit. 5 bit means this is my destination address. Next, these 5 and this 5 I will fetch and I will do this addition and then I will store in this address whatever specified in this register. So that way, this is how whatever you have written in your instruction is getting mapped to your hardware. Okay. Any question so far? No.
And can you repeat the last part?
Last part. Okay.
Yeah.
You can see this one, right? R type of instruction format. We are just discussing it. See, in this opcode here, opcode, it is defined the first 6 bit. It is defined, that is, it is specifying your opcodes. Opcodes means each opcode is basically mapping to typical operations. Now, 6 bit means you can maximum support. You can maximum support 2 to the power 6 operations. Among them, which one to choose, that is specified by 6 bit. That's why when your hardware is getting into these initial 6 bits, it is getting the idea, oh, all 0. All 0 means it is checking its opcode table. Maybe wherever it knows that this opcode value will be corresponds to which operation. It sees this opcode 0 and maybe in that design, this opcode 0 corresponds to addition. Otherwise, if it would have been all 01, all 02, then that opcode you have to specify. Then, according to our type of instruction format, come here. Next, this 5 bits. RS 5 bits. So now your hardware knows that this next 5 bit is a register that is holding the address what I will store my result. So this is my register address. Next to this one and this one is giving you two register values, from which I have to fetch the operands. Like maybe this register 2, is holding some value, maybe 2, not 2, maybe some value 40. Maybe register 3, it is holding some value, maybe 50. Then I have to do this addition that your hardware will know from this opcode, and that value 50 will get stored in this part. Okay. So this way, your hardware from this type of, because your hardware knows which type of instruction format is getting followed. Based on that, it will just read those bits and it will map those bits according to the convention. Okay. Then that way it will instruct the hardware. When opcode is 0, that means you have to perform the addition. The same instruction will be given to your ALU unit. ALU means arithmetic logic unit, where you have your addition, adder or multiply, those components. So once this your hardware is getting the information, okay, I have to do addition. So adder will be enabled. It will take these the inputs from these two registers and it will perform the addition. Okay, is it clear now?
Yes, ma'am. But like, what is the purpose of the opcode? But is it just using like whatever the function we are gonna?
Yes, of
perform?
course. The opcode is the main thing because you are sending the, let's say you are sending the data, you are storing in the register some values 40 or 50. But how will your hardware know what to do with that data? This opcode all zero, maybe they are maintaining one what to say, maybe one chart. You can think of a chart that all zero signifies addition, all 0 1 signifies maybe multiplication, subtraction, whatever you may be. You can whatever it may be, you can always check this ISA details of different processes and you will get the details. But the idea is whatever processor you work on, they will have these type of opcode mapping to operations, and that opcodes you are passing to your instruction format, and that opcode is actually giving the idea what you have to do with this to whatever code you have stored in your register or your memory. You will come to the memory part later, but what you have to do first thing is that. So that is the main purpose of opcode.
So like you have said, for the opcode we are using the 6 bits. Like there's a limit how many operations we can.
Of course,
select.
exactly. Of course, limit. That's why sometimes this is the extension, this function. You can think about some extension. Maybe this opcode is giving idea of. I'm just taking the random example, that addition or subtraction. There are different types of subtraction or different types of additions. What type of, maybe unsigned or signed, these type of what details you want to add in the opcode, that may come in this function part. Yes, your instructions may be whatever you tell. If you are telling general purpose processing also, general purpose processing means that you are supporting huge variety of instructions. And what are the instructions? That is mentioned in this based on these bit size or based on these field. 2 to the power 6 means 2 to the power 6 instructions you are actually supporting. Operations you are supporting. Okay.
But in also like this opcode, the instructions, the formats which will be using, it is also getting stored in some storage part, some register on there, right?
It is not.
Like will it be? This is also something like it is this instructions. It is a set of instructions only, like what we are gonna do. So will it be stored in a separate register or something?
Separate registers, yes. Actually, I will come to this answer. Go till the not today, maybe after tomorrow, maybe you will get this answer. Whenever I'm telling that opcode signifying that added, you remember in our first example, we have taken one example and we have told that, okay, whenever we do any specification, we try to map implementation, we divide them into some data path and control path. You remember, right?
Yes.
In our first class, we have discussed, right? There you have seen in the data path, we have some ALU parts. There we are sending the data. So data is coming from here. Okay. When we are setting this opcode means it is basically defining my control inputs. Which control inputs you will give so that your adder will, because in your ALU it is not possible for you that for one instruction always you one module you will design and add to your hardware. It is fixed, but which part, you can think in this way, which part of your ALU module you will actually enable, that input comes from this opcode. One way, it is basically defining your control inputs. That control inputs is you are giving to your ALU that, okay, now enable adder. So that control input you are defining and you are sending to your and merging with your data path inputs. That is your data, whatever you are taking from RT and RD, and you are performing operation on them. So it is just not you are just storing, but based on that you are also defining your control path also. We will be coming to it. Okay, maybe some more discussion when you see the detailed design of that. You will have a clear picture.
Okay.
Okay. So now we know that somewhere I have some instruction format, some 32-bit 1010 format. From there, dividing those, parsing those bits, my hardware understand what I have to do. Now you are storing the example we have taken there. We have only considered this register, but when actually you store, it may happen we are storing our operands in register, or we are storing our operands in memory. So when in general, this is specifically for MIPS, in some other processors also, we use a load store architecture. Like it may happen in your instruction format, you have just defined two operands that is coming from some registers. That is not always the case. It may happen that those are coming from some registers, or this is an example of registers, or that is coming from your memory. Memory means some typical address. Okay. So that means with this load instruction, what you are doing, you are storing whatever value there in this memory address to a particular register. Why? We do this register, we prefer this register access whenever we are actually performing any, we are actually performing any execution. We prefer memory register access rather than memory access, because register access is always faster compared to memory access. Okay. So that way, this is how we fetch the value from memory address and then store them in the register, and then we perform register operations.
Ma'am,
Yes.
in this, is M the address or the value at a specific address?
This one here, they have taken the address, just M. They have understood. Given some address value of a, not value of a place. This is some address. This is some address of a specific location in your memory. You have some location M. Okay. Sorry, you have some location M. Okay. So from that location M, you are fetching the address, not address, the value from this address, and you are storing that to your register R3. Okay. So here, when you are
basically, M is the address. For example,
M is the
address.
address. M is your address. M is your address. When you are, yeah.
Sure.
Clear? Hello?
Yes.
Okay. M is the address. When you are mentioning this type of instruction, load R3, R3's register is also an address. M is also an address. Okay. Just you are fetching the value. When you are operating, you are operating on the values what they are holding. Okay. Next, there are typical few examples that we have, whatever options we have, wherever we are storing. It is not that we are just storing in the registers. We are not storing in the, just a second.
Ma'am, you're not audible.
Oh, sorry. Sorry. Yeah. Yeah. Okay. Sorry. So we are coming here that we talked about different. We talked about register handling. We talked about memory handling. When we have something in the memory, we can load to the register. These are some other storage options we have. For one is the accumulator. Like here in case of MIPS, you can see these type of instructions. Add A. A means it may be some memory address. So we are from this memory address A, we are fetching some value. This is one operand. But for addition of course requires two inputs, right? So accumulator will give you the other address, other content, other operand on which actually you can apply this addition. Similarly, you can use stacks. In case of general purpose processing, we are mainly dependent on registers, okay? And of course, load store, these two we have already discussed, right? Registers we have discussed and load store operations we have discussed when we are loading to some register from some memory. Or storing means, on the other hand, we are storing some value stored in the register to some memory location. So these are loads. So these are few options we have. Next, now you can think step by step that when you are actually writing this code and you are executing, when you study this part, just think that what will happen, what may be possible. You can consider any ISA related to any processor. Then you can think step by step what will happen to your code. Well, it will come to, it is getting compiled to some binary code form, and then you are storing them and you are actually executing them with the help of some accumulator or general purpose register along with some load store. This means some part in the memory and some part in the register. Okay. Now, this is how we are storing the values. We are storing maybe in registers, we are storing maybe in the memory, we are fetching from the memory, we may be storing in the accumulator, or we may be storing in the system stack. Then next, okay, this part tells, up to this part, we are clear that how I'm storing my operands. Next, we will be talking about some addressing modes. That means that we have talked earlier. Just one example, one instance we have taken about this add example. Here we will talk, we will discuss with some more examples and more variations that how do we specify what we want to do with those operands. So there are typical few types. First one that we have already discussed, that is registered direct. We already talked about this, that we are fetching some values from this register 2 and 3 and we are storing them to register 1. Okay. Next one is immediate. Maybe that also we talked about. This immediate value we are storing, taking, maybe immediate means maybe you have stored some value, maybe 40, 50, whatever it may be. This immediate value you are operating with whatever you have stored in this register location and you are adding them to this register RS. Okay. So whenever you are actually, you will see that there is basic difference how opcode is important. We can see here. When you are actually giving this opcode instruction as add or multiply, that will directly, your hardware will directly understand you have to fetch the values from these registers. But when we are giving these immediate instructions, generally, actually this is not correct. We give these type of instructions: add immediate, multiply immediate, mul I, add I, sub I, those things. These type of operations, they have different sets of opcodes. And from those opcodes, your hardware will come to know, okay, now I have to fetch this data from this immediate part, and then I have to compute. Then this is the base plus displacement. Okay, in this base plus displacement, what we have, we are loading this. See, this is called LW. LW means this is load word. Okay. Load word means this is based on, not always, but when you are considering base plus displacement, that means you have specified some displacement and you have specified some base address. Now here, if see, it is given RS. RS means this is your base register address. From this base register address, you have specified some displacement. Okay. So initially, when we are talking about this immediate addressing, what we were doing, we are just directly fetching the values from RT, register RT. We are taking this immediate value, and now we are adding to, I mean, we are storing that to this RS. Now we are not directly storing this registered RS, but what we are considering? We are considering from this register RS, that is maybe this 2, register 2. From there, we are considering some displacement. And at that with that displacement, whatever address you are getting, whatever register you are getting, in this location, you are actually storing your data. Okay. So this is typically different type of addressing modes. One is register direct, immediate, and base plus displacement. Now, in some cases, here we have just shown that base is some register address. It may happen that base is some memory location. It may happen this base is some your PC, program counter. So from that program counter address, whatever your present address is, from there you are calculating you are adding from the present address, you are considering some displacement, and you are storing there, or you are loading from there. I mean, based on this base plus displacement idea, you are basically calculating your next address. So these are few instruction format. Next, what is important is, okay, now you know how your instruction you are going to store. You are here for this MIPS, you are storing in some 32-bit format. Now you are dividing them into some smaller bit parts, and you are understanding what you have to do, on which operands you have to do, where you have to store. Fine. You have also understand that how you will get those addresses. That sometimes it is immediate, sometimes it is direct, sometimes it is based on some displacement strategy. Okay. Now, one thing, can you answer that why this displacement type of thing is required? You already have some 5-bit or 6-bit to mention your source address or destination address, right? So maybe you have directly written that one. So why this displacement? Anybody?
Reduce the memory opcode size.
Pardon?
We can reduce the opcode size. I mean, if it is displacement is smaller value. I mean, if it is like less than the address value.
Opcode size is fixed. Opcode size is anyway your instruction set is fixed, right? You have taken a fixed instruction format, and opcode size is only you have to use a separate opcode for that. What will change if I write here displacement from
this? With this, you can use relative terms.
Exactly. Then what is the advantage of that?
Basically, you can access a larger set of memory without increasing the size.
Exactly. So that is the requirement. Because whenever you are specifying, whenever you are restricting your register, the bit sizes for that particular field to 5-bit or 6-bit, maybe that is not sufficient. So how will you actually address some larger space? So for that, you are applying this displacement strategy. So this is for just increasing your possibilities. Next, this is the memory organization. Memory organization may be in two ways. One is by byte addressing. Like when you are storing your data or storing your instructions maybe in your memory, in which way you will store. One way is that you are storing in form of bytes and storing in different, and you are dividing whatever instruction you have in you're dividing them in the form of bytes and you are storing them, and that is the byte addressing. You may have word addressing, whatever possibilities you may have. We will see later this word addressing and all. So whatever possibilities you have, byte addressing, word addressing, you should know prior, because otherwise you actually cannot do that mapping, or your hardware cannot do that mapping to fetch your operands or fetch your instructions. So know your memory, how it is organized. It is also very important for good developers or good software designers. So we will come to this. We will discuss, we will take a separate class for this memory organization. So whatever we have discussed for so far, that MIPS, we know this is a fixed 32-bit instruction set. I have taken MIPS because this is very specific and this is very general and very basic. So you can think now I think you have some idea that when you are actually having this type of compilation code, some machine code, and you have some other processor, maybe that may be some 64-bit, that may have some different instruction formats. Here you can see that your opcode is 6-bit. Maybe those instruction designers, they have thought that no, 6-bit is too less, we cannot actually support most of the instructions. So let's improve that to 6 to 12 bits and support some more operations. And maybe some register size or way of formatting, those are different. Those you can find in the detailed specification of any processor. But I think this discussion will give you the idea how to start thinking of reading that instruction format. What are the fields you will read, and from there, those fields, how the instruction is actually going to your hardware. Okay. Next, one quick discussion. What type of instructions are possible? One is, I think, those things, whoever has written that NEC code or Java code, they already use some operators. So from there, you can actually get the idea what type of instructions are possible. Not all, but arithmetic operations, you know, whenever you are actually writing some instruction related to arithmetic operation, you must, and now you have the knowledge that that is getting supported by some of your backend hardware. Otherwise, that is not possible. Then some logical operations. This data transfer, this is typically for loading and storing. When you are fetching the data from memory to some register or storing the data back to the, back to the memory. Next, one thing is left, that is branching operations. You are writing in your design, if A less than B, go to this step. If C less than D, go to this step. Now this branching also need to be handled by your instruction format and backend in your hardware. So there, what we see, whenever you have written some instructions, instruction 1, 2, 3, you have written and you have related the codes for that. Now, in your backend hardware, you have PC. PC means program counter. This program counter actually storing this instruction, and it is actually traversing it is checking what is there in your next instruction, and it is fetching that this PC is actually program counters is fetching those instructions. On top of that, the next level of hardware is doing instruction decoding and execution and all. So initially PC is actually, you can think that PC is traversing in your instruction memory. Instruction memory, where you have step by step stored all your instructions, and from there program counter is fetching one by one. That is the instruction fetch, and from that is basically nothing but some values of 1010 and all, and from that values you are just checking what are the opcode part, what are the operands part, what are the storage part, everything, and you are getting it back. Similarly, you have typical instructions for jump, that is branch if equal. In that case, whenever you are getting, whenever I should say your hardware getting the opcode related to BEQ, branch if equal, then it is checking whether these two values in these two registers, in this register 1 and register 2, whether they are equal or not. If they are equal, it is jumping as per the specification, it is jumping to this location. Okay. So these are how the conditional branching techniques are handled the backend hardware. Similarly, there are different instructions, BQ, B, not equal, equal, whatever you write, based on that there are typical instructions possible, the opcodes possible, and that opcode is giving the ID. Similarly, you have the jump that we have already mentioned, that jumping opcode is there, and this target is showing where you will jump. So these are the few instructions, and branching, jumping together is possible. So now we are getting this idea what are the different address modes and the data and control transfer. So see, from here you can see that these are different addressing modes, whatever we have discussed so far. We have discussed immediate addressing, we have discussed register based addressing, where we have this RS, RT and all. We have discussed base addressing, where you can see here this you have some address, maybe that is your displacement and this register value. With that together, you are considering that memory address, and from there you are fetching those bytes. Okay. So when we are considering this base or relative type of addressing, these are one extension of that, where you are storing your immediate address in PC. You are considering your base address in PC, and from there you are considering some displacement. That we have actually seen in our previous example here. You can see it. Just taken one example. This one. See, this one is your PC relative addressing. PC relative means base address is by default, it is in the PC program counter. From there you are considering this displacement. So these are different addressing modes possible in NIPS. Okay. Zero direct addressing, where you are just considering some operation with PC and there you are jumping. That means initially when we have talked about branching operations, we have jump operations, we have considered that whenever jump output you are having, you are just jumping to that particular address. But here you can see not you are jumping to that particular address, but you are actually considering some operation with this PC and that particular address, and from that address you are jumping. Okay. So these are few typical types of addressing modes, and from those addressing modes, how you are actually accessing the memory. You can see here everything is summarized, and based on different operations, these type of how the instruction you can form and what are the possible extensions, those are given. So you can try yourself this maybe later on. that how we are mapping. Maybe some of you who have done the microprocessor lab, they are known to this, but you can check this. There are some alternate architectures, but we are not coming to this. We will talk it maybe in the next day. We will discuss about pipelining and parallelization more, and then we will talk about this. Okay. So this all we have talked about MIPS instruction set architecture related to MIPS. This is just an example we have taken. I'm again telling, and you can think any processor or its instruction. You can actually, I mean, I want to say, analyze the instruction set architecture of any other processor in the similar way. Okay. Is there any question till now? Hello? No question. Okay. Okay, then so we are here. We have just discussed up to this part. Maybe tomorrow we will discuss about some typical embedded system domain related processors. Those are microcontrollers. We will talk about what are the specific features of DSP processors and why they are suitable for signal processing, DSP signal processing. Then we will move to some idea about graphics processor. Then we will move to how we can actually apply. That is very important. Parallel processing. Concept of parallelism in this type of processors. That is, we will discuss pipeline in detail and what are the hazards possible in the pipeline. Okay, so that's all for today's discussion. Now I'm uploading one assignment to your Google Drive. You just check it out. This is a small, you have to draw a small FSM. Okay, so you just draw it, take a snap of it, and now within 20-30 minutes you just upload it. Maybe you can upload it you can mail me back, or if possible, no need to upload it here. You can mail me back. Okay. In between, I'm checking whether I can upload it here because it was taking time from my part. So if possible, I'm uploading it that to also in this Teams assignment part, and then you just upload your response here. Okay.
Ma'am, deadline?
Just now, 20 minutes. Immediately do it and upload it.
Sure.
Okay. Yes.
Ma'am, you're uploading the one on Teams as well and the drive as well, right?
No, I am uploading the assignment now to the drive. Okay, you try to continue with it. Then I'm trying to upload that to the team so that you can send your response to the team. Okay, sure. I was just checking that out, but it was taking some time. I don't know why. If that is not sorted out, then you just mail me your answers. You just take a snap. You do it in your pen and paper. You have to draw a FSM basically, and some details you can write. What are the states and what are your assumptions about the transition conditions, etc. It's a very, very small assignment. You do it, upload it, and send me by mail. And in between, I will let you know if I can upload that to this Teams assignment part. Then you can directly upload there. Okay? Clear?
Ma'am. Yes, ma'am.
Okay.
Ma'am, by when will I submit the assignment? Today I joined the class first time.
Ma'am, will you be uploading the assignment in Teams as well or only on the drive? Excuse me, ma'am.
Yes, hello. Yeah, can you hear me? What I am telling, I am trying to upload that to Teams, but I have already uploaded that to the drive. You start working on it. In between, I'm trying to upload that in Teams so that you can submit it Teams. Okay, it was giving some problem. If I can do it, otherwise you will submit. You can mail me. You just take a snap of it. Just mail me. Okay.
Thank you, ma'am.
Ma'am, where in the drive? Which folder?
This one, the ESDB 22, the whatever, I mean, you have your study materials, right? The same folder. I'm sharing it again.
Ma'am, there are like 4 in the 2021, right? ESDV underscore 2020.
ESDB 2020, yes, yes. There you can see.
We are not able to find, ma'am. Where it is?
ESDB, I'm sharing the link again. Okay.
You can see now. You can see now.
You can see, just check it out or just upload it. ESDB 2020 folder. The just only one folder I use. There is, you can see the assignment one. Can you see that now?
Yes, ma'am, we can see.
Yes. I've also shared the link, link of the drive folder. Okay. You start working and submit it. I'm trying to upload here also. Sorry.
Ma'am,
Yes.
I have a doubt in the question.
Yes. Tell me.
So the first sentence it is given, it is like a sample input, right? Given two strings
Yes.
and a
Any
pattern.
input, any test stream input. I mean, for any test input, just you have to check that pattern the pattern. Sample
Oh,
input means it's a text. Okay.
okay. So that
So in the text,
second
whether
one is
the is
also,
present. Yeah. Pardon.
first one draw the FSN to identify the in the present is present in your input. Is it same for every? I mean that the keyword is same for every case, or should we take input for that one also?
No, the idea is you have to check. You will take one input stream. Okay. For any input stream, you have to check. You will design the states in such a way that you will identify is this pattern, if this pattern the is present or not.
Okay.
If that is present, you have to give the count of that. How many times it is present in the
Okay,
same
ma'am.
FSM. No need to draw any separate FSM. Okay.
Okay. So
Now think
that
how will you draw the states? Yeah.
that the is constant. Only we are taking the input string. That the
The is
it
constant,
always
exactly.
okay.
For just you draw for the and
Okay.
and another thing maybe I have not mentioned there, that I mean no need to think about this case specific thing, case sensitivity. Okay, capital,
Okay.
small, and those things no need to think. Just the
Okay.
okay.
Ma'am, one question.
Yes,
At the date signifies the end of the text, right?
end of the
At
text.
the
Yes. Like
Ma'am, so
you
that
get end of file or something like that, right? So
yes,
that for to handle that you have to consider ASCII or something. So I have not no need to go to that part. Just think that if I get some that special symbol, that signifies that that is your end of file or end of text.
ma'am,
But
where can I
always we
submit?
had
Hmm?
always
Pardon?
we have to consider at symbol, right? I mean, will there be any case whether the string will end without the end symbol?
No. Just this is the assumption. I know this is a very simplified assumption. Just I have given this to simplify your example. Consider if that special symbol is there, that symbol is not present within your text, and that symbol is there at the end, and that symbol is present, that implies that that is the end of your text. Like that is end of file or end of text you are considering.
Okay.
Okay.
Ma'am, can you please tell me your email ID so I can share my solution with you?
Okay. It's you know my email ID. Oh, you don't know. See, okay, I will message. The chat I'm writing. You can upload here also. I have uploaded in the Teams. Okay.
Okay, ma'am.
You can take a snap and you can just submit there. I will download from there and I will check it out.
Okay.
Hello.
Yes.
Yes, ma'am. One doubt. Like we have to consider general input, like the string, the given string only, or like in general any string.
Any string.
Okay.
For
Okay.
any string, only you have to check whether the pattern
Yeah.
is there or not.
Okay. Okay.
Okay, the
Like
string
pattern is
I mean, yeah, for any string,
pattern is fixed, but the string, like string is a general thing.
string is the general thing. Yes, the string will be your input.
Okay, got it, ma'am.
Ma'am, I have submitted the assignment. Have you got it? Hi, ma'am.
Yes, I got it. Okay. Based on whatever Akashjit submitted, I want to clear one thing. Okay. With all of you. That whenever you are considering the input, how that input will come, it is a text. Okay. It may happen that together the will not, whenever you are processing maybe alphabet by alphabet. Okay. It may happen that whenever T is coming, after that some other letters with T is coming. It is not it. Yeah, I mean, we together. If you are handling with the, that is not typically always correct. Okay, so try to think in this way whenever you're considering that input stream or your input text. You consider it them processing by alphabet, and then you think whether you are getting that pattern or not. Okay, Akashit.
Okay, ma'am. I'm resubmitting it.
Yeah, you just try and modify.
Ma'am. Ma'am,
Yes. Yes.
have like if there is a word like these, I mean, should I consider it as a th inside that word?
What is that? There is
Like
a
if there, if I take a word there, should I consider that th in that pattern
yeah.
inside the?
Anyway, the THE.
So
The pattern.
th, I mean, it shouldn't be an independent word. So even if it comes inside another
So
word,
you
it
can
should
tell
be.
you. I mean, what I can say. If you're thinking, I know. According to the question, you can take THE wherever it is possible, and you can give the count. Okay.
Okay.
And if you are thinking, I understand that you are thinking about the article the, right?
Yeah, there.
For
So
that,
it's
you have to consider after that there should be a space.
yeah,
So
yeah.
if you are considering that also, just write in your assumption, then I will check accordingly. No problem.
Okay, okay.
Okay.
Ma'am, we have to go for space case ma'am after the space.
See, think about your any text, right? It may happen like your any word like let's say thesis. Okay, there also THA is possible.
Yes, ma'am. Yes, ma'am.
THA is possible. But if you are actually you are thinking about the article the only the, for that you have to consider the then a space. Okay, so whatever assumption you are making, just write it clearly and I will check it according to that. Sridhar, maybe you have submitted. Are you there?
Yes, ma'am. I did a mistake. I'm submitting
Yes,
it
yes,
again.
yes. You just check about the
Yes,
company.
ma'am.
You check it out. Okay.
Yes, ma'am. Yes, ma'am.
Yeah.
Excuse me, ma'am. I sent my assignment through email. Have you received it?
Checking.
Ma'am, I have also sent one.
Yes. Okay. Yeah. You can upload. You all can upload in as here also. I mean, this Teams part. Can you upload it there?
No, I'm trying actually. Actually, there's some network
Ma'am,
problem.
yes, we can upload on the team.
Yeah.
Okay, no problem. Otherwise, I will take it from here. Whoever can upload, just upload there, and rest. Whoever submitted, it's fine. No need to do the. Or better, you upload there. Everybody will have in the same place. We will have all the assignments in the same place actually. So better upload in Teams. So those who have already submitted and finished, you can log off actually. Okay. We will discuss that next day.
Ma'am,
Yes.
I had
Yes.
ma'am, I had turned in just now. Can you check whether it is legible?
Okay. Don't worry. We will discuss one-to-one when Friday there is a Viva and discussion, right? We will do it one-to-one discussion.
Okay.
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 So you all just finish and submit it. I have just set the time here in this team up to 10 today. And those who cannot finish within that time, whenever you finish, just send your answers over mail. Okay. So I'm ending this meeting here. Is there any more questions? Any other question?
Ma'am, can you please extend the time to 5 or 10 minutes more?
Okay. Sorry. Okay, so I updated the time in that assignment part. And still, if you need time, just whenever you finish, just send me a mail. Okay, so I'm ending this meeting here. Is there any more questions related to the assignment or something?
Ma'am, lecture slides.
Lecture slides I have already uploaded, right? The last slide, maybe it is pending. I will upload it. The video lectures I have uploaded. Rest I will upload.
Ma'am,
Just let me know. Yeah.
yeah, at the end, are we transitioning? I mean, are we ending the state space, or are we waiting for? I mean, even after getting it, if after that we get some more letters, are we checking that also?
Can you come again? Yeah.
You said like when it is at, we will give the output.
Yeah. When you will give the output.
Yeah, but if something is there after that, should we check that also, or are we terminating there?
No, whenever you are getting that end character that I have mentioned, right? One specific character that is indicating that is the end of your text. So whenever you are actually getting that character, that indicates that no need to check further. So that is the end, and then that will give you the final count. I mean,
Okay.
from there you can give the final count.
Okay.
Clear?
Okay.
Ma'am, in the assignment, I did one small mistake, ma'am. I'm submitting it again.
Okay, no problem. I have extended up to 11 here in the
Okay,
team.
ma'am.
So you can submit there. Otherwise, you can after that you can submit over mail. Okay.
Your mail, ma'am. Your mail. Ayantika@80. That mail.
Ayantika 123. No, I have given in the chat. Send to my Gmail. Otherwise, IT mail will be too much. I mean, shortage of space.
Okay, I am uploading in MS Team only, ma'am.
Pardon?
Ma'am, I will upload in MS Teams only.
Yes. And the rest you can upload. Yeah. I mean, try to upload within 11. This is a very small assignment.
Yeah. Okay, ma'am. Just 5 minutes, ma'am. That one small mistake.
Yeah.
Just
Upload till 11. Yeah.
Okay,
try to finish within them. So I'm ending this call here. Okay.
Ma'am, one question, last question.
Yes.
On Friday, the doubt clearing class that you said, from when it takes place, the time.
Friday there is already one class. We have one additional slot. That this is actually, see, in this semester we have the usual slot plus this one 8 to 10. This is our V slot for V additional slot. Okay. So we are taking the class here, and that Friday class we will be using for that Viva and all. Later on, I will take one class test also. That time also I will use those type of slots. Okay.
From when that class starts, can you please tell me on Friday?
You don't want the class timings? Okay.
Yes.
Okay. That is a 2 to 4 maybe, or 3 to 5. That was according to the slot. I will check and I will send you mail. Okay, to all of you.
Okay. Thank you.
Maybe it is as far as that is 3 to 5 or 2 to 4. That is the usual V2 over V3 class slot. I will check and send you a mail. Maybe I will share in this group.
Ma'am, will it be an individual Viva?
Yes, individual Viva.
Sure, ma'am.
Okay. I will send you the timing slots also. I mean, which time to watch, which time tentatively you will be asked questions. So you can be online at the time only. So that will be good. Okay.
Okay, ma'am. Thanks.
Okay. That's all. Okay.
Thank you, ma'am.